Hello, everyone. Welcome back. Glad you can make it. So we're going to start today just by reviewing the things we've been covering over the past week, past 2 weeks. We've been focusing on integration. Integration is probably the second most important topic of calculus. Mainly limits, derivatives, and integrals are thought of as kind of the three big components that make up calculus. So we've covered limits, we've covered derivatives, and integration is the third big idea of calculus. And let's go over what integration really does to a function. So it is an operation, kind of like how you can take the derivative of a function, you can take the integral of a function as well. Derivatives are pretty simple, they're pretty grindy. There are all these rules we use to take the derivative of everything. We have the power rule, product rule, chain rule, quotient rule, all those different rules for derivatives. But integrals are much trickier. And I say that a lot, but basically it's easy to learn. If you're willing to put in the time and the effort to learn how to do complex integrals, you'll be in pretty good shape as long as you have a good attitude going into it. I will say this, when I first took calculus, I think about a third of the class dropped out by the time we got to the integral section. So it is tough. I just want to say that it is tough, but we can get through anything in this class. I have faith. So back to the main concept of integration and what it does to a function. So derivatives tell us rate of change. A derivative tells us the slope of a tangent line at a particular point in the function. That's just the instantaneous rate of change of a function. An integral tells us accumulated change. So I'm going to draw some generic function. And suppose we want to figure out how much change has accumulated. So this is kind of a weird example, but suppose you're driving on the highway. Suppose this is a graph that shows your speed or velocity. V of t is velocity with respect to time. So time could be in minutes, and then the velocity could be in, I don't know, miles per minute. So we're going to start at this point right here. And let's say that when we start the timer, we're already traveling at a rate of, I don't know, maybe let's say we're traveling at a rate of 35 miles per hour. And then we accelerate a little bit. We get onto the on-ramp of the freeway. We get to 40 miles per hour. We slow down a little bit. We slow down and anticipate trying to change our lane. We want to get into a fast lane. So we dip a little bit, speed decreases, and then we're able to go to the fast lane. And then this could be, I don't know, let's just generalize. This could be maybe 50, 55 miles per hour. So what if you wanted to figure out how much distance you traveled from the beginning of the timer all the way to the end and we stop? So this is what an integral really tells us. An integral tells us how much change has accumulated. So if we wanted to figure out how much distance we have traveled all the way through from start to finish, we would just set it up like this. We would do the definite integral of v of t, where v of t is going to be our velocity function. And of course, we start at 0, and you can end whenever you want. I'm going to just generalize it, maybe call this b, where b could be any value. So integration is just a measure of the accumulation of change of a function. And when we first started learning about the concept of integration, there was a lot of talk about Riemann sums. And Riemann sums are an interesting way, for lack of a better word, it's an interesting way to approximate the area under a curve. And remember we did that with rectangles. Remember we did that with a few pre-chosen rectangles that all have the same width. And that width is delta x. And I should probably move them a little closer together. So the Riemann sum is the precursor to the process of integration. Before knowing about integrals, the best we could do was an approximation. So if we drew each rectangle so that the midpoint of the rectangle goes through the height. So for example, this one goes through the height, and this one, and then this one. I know it's not perfect. I'm a really poor artist, but I'm doing the best I can. So each of these goes through the midpoint of the height of the rectangle. And the idea is, if we have a rectangle for each of these specific time intervals, if each of these have a distance of delta x, a width of delta x, then this would give us a pretty rough estimation for the total accumulated change. And then we found out that actually we can get a perfect measure of the accumulation of change by doing the integral. The Riemann sum, it's good for an approximation, but you just can't beat having the exact value, the 100% correct value without any deviation. And that's where integrals come in handy. An integral just tells us what the area underneath this curve is. So if each rectangle were to get smaller and smaller and smaller, and if we were to fit an infinite number of rectangles in this space, the integral is what tells us the total area under the curve, the total accumulation of change. So let's review a little bit on how to bridge the gap from a Riemann sum to an integral. And I'm going to be using an actual example from the textbook. So let's say we have a function, we have f of x is x cubed minus 6x. Oh, my drawing tablet picks the perfect time to stop working. Very frustrating. Sorry about that. And don't know why this happens. Might have to go buy a new one pretty soon. It's getting pretty old. There we go. It's back up and running. So we have a function. We have f of x is x cubed minus 6x. This is our function. And we want to take the integral, but before we take the integral, we want to just find an estimate for what we think the value of the integral should be. So we're going to use a Riemann sum to get this estimate, to get this approximation. So remember with the Riemann sum, there are a few characteristics we have to consider. So with the Riemann sum, we have a number of subintervals, and we have a starting point, an ending point, and a number of subintervals. So that would be n. N would be the number of intervals that we break a function up into. A would be the starting point, B would be the ending point. So we're going to do this one with the right endpoints. We're going to do RHS, a right-hand sum, right-hand Riemann sum. And these are just values the book gave us to work with. So we're doing a right-hand sum. We have A is 0. We have B is 3. And we have N is 6. So we want to start just by doing a quick sketch of this function. And I might want to modify the axis a little bit and make it look like this instead. Makes it a little bit easier. So we have an intercept somewhere between 2 and 3. Somewhere between x equals 2, somewhere between x equals 3. So when x is 3, y is going to be 27 minus 18, so that would be 9. We have the point 39. We have an intercept right around here. And then it reaches a local minimum, or I think actually it's a global minimum. It reaches the minimum and then it comes back up to the origin, and it looks kind of like this. So we're going to have a part that's positive. We're going to have a part that's negative as well. So our goal is to make a right-hand Riemann sum, an estimation of what we think this integral might be. So we have A is 0, and we have B is 3 right here. So our goal is to get an approximation for what we think all of this area is going to be, the combined area between the part that's negative and the part that's positive. So what we want to do is we want to decide where we're going to make our rectangle. So we have, it looks like if we go 0 to 3, we're going to have just 1, 2, 3 on the x-axis, but n is 6. So we want 6 rectangles. So that means we just want to take every interval and split the interval up into 2 more. So that we're going to have 2 intervals right there, and then 4 intervals, and then 6 right here. Going from A to B, we would have 6 intervals. And it's a right-hand Riemann sum, which means we want to draw a rectangle at every point, and we're going to extend the height until until the right-hand side of the rectangle reaches the function itself. So we're going to do that 6 times. It's going to look like this. Third rectangle will be right around here. And then we have a fourth one and a fifth one. Well, this one is a little tricky to do because we're actually going to want to go the opposite direction for the height of the rectangle to touch the function. So we're actually going to want to go up and not down for this one. And then our last rectangle will be like this. So that's what our Riemann sum would look like. So let's see if we can get an approximation for what we think this is. But before we continue, we want to decide delta x. So delta x is going to be just the base of a rectangle. And they're all going to be the same. All 6 of them are going to have the same base. They're all going to have delta x as the base. So we can quickly find out what delta x is. Delta x is just b minus a over n. So we have 3 minus 0 over 6. And that is just going to be positive 1/2. So every rectangle just has a base length of 1/2. All 6 of them have the same base. So now we just want to figure out what the heights of each rectangle are going to be. So this first rectangle over here, call this rectangle A. So remember that the area of a rectangle is just base times height. So we have a base of 1/2 times the first height of rectangle A. And then we're going to have 1/2 times the height of rectangle B. And we would just do that until we get to the very last one. So that would be rectangle F. But because they all have a 1/2, we can actually just factor out a 1/2 from all 6 of our terms. We can make this 1/2 height of A plus height of B plus height of C plus height of D plus height of E and then plus height of F. So let's see if we can find the height of rectangle A. We want to find this part right here. We want to find this vertical distance. So to do that, we just want to find what happens when we put x equals 1/2 into the function. So for f of x, we're going to make this f of 1/2. So we get 1/2 to the 3rd power minus 6 times 1/2. So 1/3 to the 3rd power is 1/8. We have 1/8 minus 3, which is the same as 1/8 minus 24/8, which is negative 23/8. And then we want to do the same thing for the next one. So our next x value is going to be x equals 1. We've already done 1/2. So x equals 1 is going to be our next value. So let's see what happens when we plug in 1 for x. So f of 1 is just going to be 1 to the 3rd power minus 1. So that would just be negative 5. So we have negative 23/8 minus 5. And then we want to do the same thing for all of them, but I don't really feel like it's wise to spend all the time doing all of them. So I'm just going to show you guys what the answer is because I've already worked this one out. So if we were to do this, if we were just to keep going until we have all of our values submitted, we would get a total area of about negative 3.9375. And it doesn't look like it makes much sense because an area is supposed to be positive only, right? I don't think I've ever heard of a house that has a negative square footage. Area should be one of those quantities, kind of like length, where it just doesn't make much sense if it's negative. I mean, I've never seen a ruler that has a negative length on it. So area should be the same thing. But the thing is, there is kind of a fine distinction between the value of an integral and the true area under a curve. So if they asked us for the area, we would use some special techniques in order to make sure we get the accurate area. If they asked for area, we would take all of this in the negative part and we would turn that positive. We would take the absolute value of everything in the green box and then we would just add it to whatever is already positive. So if they asked for area, that's how we would do it. But the thing is, they only asked for a Riemann sum. So area can only be positive. A Riemann sum can actually be positive and or negative. So that's why our thing ends up being negative, because this thing in the first box, the amount underneath the x-axis, is much higher in value than what's above the x-axis. So that's why our answer ends up being negative for this one. It's a Riemann sum and not an area. So now let's actually apply calculus and get the exact answer. It's much easier and much faster because we don't have to mess around with fractions and do all these tedious calculations. Calculus just makes it much easier, and we get a much more accurate answer. That's why it's such a really powerful tool to have in your disposal. If you want to study science or engineering or economics, it's indispensable. So let's work with the same function, but this time let's find the integral and see how close we are with the Riemann sum. So we're going to have the same bounds. We're still going to go from x is 0 up until x is 3. So 0 and 3, these are the limits of integration. They're just the starting and ending points of our interval that we're integrating over. And then f of x, our function, is going to be the same. So we have x cubed minus 6x. And you can think of an integral as kind of like a sentence. You always start a sentence with a capital letter, and you always end with a period. An integral always starts with this integral sign, and it always ends with dx. We call that the differential. Dx is the differential. The function that we're taking the integral of, we call that the integrand. Integrand is just a function. So in this case, the integrand is x cubed minus 6x. That is what we're integrating. So we have to take the antiderivative. So in order to do that, we want to identify our first exponent that we have in our first term. So we have x to the third term. So what we want to do is we want to add 1 to this exponent, and then we want to divide by the result. So we're going to make this not x to the third, but x to the fourth power, and then we're going to divide by 4. And then we're going to do the same thing with the other one. So we have an invisible 1 right there. Whenever we don't have an exponent, it's automatically an invisible 1. So what we want to do is we want to add 1 to that exponent. We want to make it 6x to the second power. Still minus, it's still going to be a minus 6x, but we're going to change the exponent into a 2. And then we're going to divide by that very same exponent. We're going to divide by 2. And whenever we take the antiderivative, we no longer have the differential. The differential goes away. And we no longer have the integral sign either. That also goes away as soon as we've taken the antiderivative. So what we need is we need brackets. We always enclose the antiderivative in brackets. And then if it's a definite integral, which this is, we have limits of integration. So that's how we know it's a definite integral and not an indefinite integral. So we're going to make this go from 0 to 3. So we're going to just plug in our endpoints and see what we get. So we're going to do, first, we're going to evaluate this antiderivative at 3. So we have 3 to the fourth power because x is 3. And then we have minus 6 times 3 squared over 2. And then I want to do the exact same thing with our lower bound. Our lower bound in this case is 0. So we always subtract. Whenever we're evaluating a definite integral, we always do the antiderivative at the top value minus the antiderivative at the bottom. We always subtract. So we're going to have 0 to the fourth power over 4 minus 6 times 0 squared over 2. So let's see what we get. So we have 3 to the fourth power, which is 81. So we have 81 over 4. And then we have 9 times 6, which is 54. And then 54 over 2 is 27. So this is going to be minus 27. And then we're going to subtract basically nothing. There's nothing but 0 left in the other group. And there is still a bit of calculation involved. We might have to find a common denominator and combine fractions. But compared to what we're doing with the Riemann sum, this is much better. I'd much rather do this than deal with a Riemann sum. So our common denominator is 4. We're going to make this 54 over 2, and then we're going to make it 108 over 4. So we have 81 minus 108 over 4. And the answer we get is going to be negative 6.75. So we got something a little bit different than what we had with the Riemann sum. With the Riemann sum, we got negative 3.9375. So we got a negative answer for both, but the integral is exact. It's the exact answer. This isn't at all an approximation. This is the exact value of the area under the curve, considering positives and negatives. So as you can see, with a function like this, a Riemann sum with these conditions may not be really effective. I mean, maybe if we made delta x smaller, if we made delta x, I don't know, instead of 6, what if we made it 12 or 18 or 24? The more rectangles we have, the closer and closer the Riemann sum would get to this answer right here. So the integral is always preferable to the Riemann sum. We always want to get as close as we can to the integral answer. All right, so that's kind of just a quick refresher on how an integral is related to the concept of the area of a function under a curve. So let's try another definite integral. Suppose we're trying to find the integral of e to the x, and we are going from 1 up to 3. So this is something we know how to do. Whenever we're dealing with something like this, we want to, well, when I was first learning calculus, I thought it was helpful to make a list of the derivatives of a function. So we have e to the x. The derivative of e to the x is e to the x. If you take the derivative again, you still get e to the x. So moving down is taking the derivative. Moving up is taking the integral. So if we want to find the antiderivative of e to the x, we just want to go backwards, and the antiderivative of e to the x is also going to be e to the x. This is integration or just taking the antiderivative. The antiderivative of e to the x is e to the x. So this is our antiderivative. We're going to evaluate this at 1 to 3. So we're going to go e to the x evaluated at our topmost endpoint, and then we're going to subtract e to the x evaluated at our bottom endpoint. And then there's not much else we could do. I think the most we could do with something like this would be to factor out a multiple of e, so we would get e squared minus 1. And then if you wanted to take it even further, we could use difference of squares factoring to simplify our right factor of this. We can make this e times difference of squares. This would be e minus 1, e plus 1. This isn't necessary. I mean, technically, what we have right here would be technically correct. It would be fine to leave it at this, but for some technical calculus problems, like something you might find on the AP exam, they might want you to find the intercept. So if you wanted to find the intercepts, it would be much more helpful to put it in this form right here, because it makes it so much easier to find where the x-intercepts are if this is a function that we're trying to graph or factor in any ways. So it really just depends on the context of the problem when you're deciding if you want to just leave it like this or if you want to